Welcome to this explainer. Today we're diving into the incredibly fascinating world of predicting photon behavior using the Monte Carlo method. We're going to explore exactly how abstract probability shapes real-world medical physics. It's a really cool concept, so let's just jump right in.
Now, you might be wondering, what does rolling a dice have to do with fighting cancer using radiation? I know, it sounds kind of like a strange comparison at first, but it turns out it's literally everything. Simulating 1 billion microscopic dice rolls is exactly how we predict the paths of invisible photons in medical physics. See, because we just can't perfectly map out the journey of every single photon as it passes through human tissue analytically, we have to rely on probability. We use advanced algorithms to roll virtual dice over and over again to figure out exactly how much radiation dose is being delivered.
Here's our roadmap for the explainer today. We're going to cover the Monte Carlo method, setting up the simulation, rolling the virtual dice, the 4 photon interactions, and finally, running the code.
All right, let's start with section 1, the Monte Carlo method.
At its absolute heart, the Monte Carlo method is a stochastic method. And what that means is it utilizes probability models and random sampling to estimate complex deterministic quantities. And for us, that quantity is radiation dose. This method is used everywhere, right from predicting the weather to modeling the stock market. But in medical physics, it helps us compute things that are either incredibly difficult or, honestly, completely impossible to solve using simple analytical equations.
So every Monte Carlo simulation actually relies on 2 critical backbones. First up, you've got a massive sequence of random number generators, or RNGs. Simply put, without RNGs, absolutely no radiation transport can be modeled, period. Second, you need a method to actually sample from those probability distributions. We're talking things like inverse transform sampling or acceptance-rejection sampling. How you generate those numbers and how you sample them, well, that ultimately makes or breaks the accuracy of your entire simulation.
But here's a really fascinating problem. Computers can't easily generate true randomness. It's just not how they work. So we rely on pseudo-random numbers instead. These are sequences generated by algorithms that just appear random enough. And a super crucial concept here is the period. Basically, every pseudo-random generator is going to eventually repeat its numbers. If that period is too short, the numbers repeat right in the middle of our simulation, totally ruining the physics. That's exactly why advanced Monte Carlo codes, like EGSnrc, use highly specialized generators like RANDMAR or RANDX, because they have incredibly, almost unfathomably long periods.
Moving right along to section 2, setting up the simulation.
Before we can drop our hero, the photon, into the simulation, we literally have to build the physics rules of our virtual environment. And we do this using highly curated web-based databases. For example, we use the NIST XCOM database to grab our photon cross-sections and attenuation coefficients. Then we use EGSnrc for electron stopping powers. And crucially, we lean on the EPICS 2023 libraries like EPDL and EADL to get incredibly detailed atomic form factors and binding energies. You can't just calculate these on the fly. You absolutely must import this physics data directly into your simulation code so your virtual world behaves exactly like the real one.
Once that world is perfectly built, we introduce our particle. And 7 is the magic number here. Every single photon dropping into our simulated geometric phantom requires exactly 7 parameters to be tracked at all times, no exceptions. It needs an energy value, it needs an x, y, and z coordinate for its exact position, and it needs 3 direction cosines, ux, uy, and uz, to tell the simulation exactly which way it is pointing. If you simulate 10 million photons, well, that's 70 million parameters loaded into a massive phase space file. That brings us to section 3, rolling the virtual dice.
Now that our photon is loaded up with its 7 stats and placed right into the phantom, it's time to let it fly. The very first thing we need to know is just how far the photon travels before it hits something. We call this the mean free path. It's the average distance a simulated photon travels uninteracted between successive collisions in a given medium. To figure this out in the simulation, we generate our very first random number and use inverse transform sampling. This samples the mean free path probability distribution to spit out an exact distance. The code then basically teleports our photon that exact distance forward.
But wait a second, how accurate is that random dice roll? Well, the crucial point here is the sheer volume of histories required. Look at it this way. If we only roll the dice 10 times, meaning we simulate just 10 photons, our error rate compared to theoretical math is a massive 30%. That's huge. But the law of large numbers is totally on our side. If we ramp that up and run 1 million histories, that error shrinks down to virtually 0, literally just 0.05%. So relying on Monte Carlo really means committing to massive computational scale.
Which brings us to section 4, 4 photon interactions. Okay, so our photon has traveled its mean free path, and bam, it's hit an atom. What happens now? Well, the simulation uses a cumulative distribution function, or CDF. It checks our second random number against the probabilities of 4 possible boss fights, if you will: coherent scattering, incoherent scattering, the photoelectric effect, or pair production. The simulation basically stacks these probabilities up from 0 to 1. Wherever our random number happens to land, that strictly decides the physical fate of the photon.
Let's say the dice lands on coherent scattering. The photon bounces off the atom elastically. This means no energy is lost, only its direction changes. Now, simple models might use Thomson scattering, which assumes a single free electron. But we know in reality, electrons are bound tightly to atoms and their electrical fields interfere with each other. So our Monte Carlo simulation must use the much more complex Rayleigh scattering model instead. Rayleigh actively accounts for this interference by pulling atomic form factors directly from those EPDL tables we talked about just a minute ago.
But what if the dice lands on incoherent or Compton scattering? In this scenario, the photon transfers some of its energy to an electron, which then recoils, while the scattered photon flies off with less energy. Again, a super simple simulation might just use the Klein-Nishina theory for a free electron, but a high-fidelity Monte Carlo simulation, it models a bound electron. It accounts for the electron's binding energy and momentum. And this is absolutely vital because bound electron effects actually cause energy broadening of the scattered photon. That is a crucial detail if you're simulating something like nuclear medicine detectors.
Now, if the dice selects the photoelectric effect, our original photon is destroyed entirely, gone. It gives all of its energy to a bound electron, which then gets forcibly ejected. But the code's job isn't done yet. The atom is now missing an electron, making it highly unstable. So the simulation must now calculate how the atom violently relaxes. It actually rolls the dice again to see which higher-level electron drops down to fill that hole, and whether that specific drop emits a fluorescent X-ray or maybe kicks out another particle called an Auger electron.
Finally, if our starting energy is really high, we're talking over 1.02 MeV, our dice roll might trigger pair production. This is where the photon interacts with the intense field near the nucleus and literally vanishes, converting its pure energy into matter. It spawns a positron and an electron. The simulation then uses the Bethe-Heitler formula to calculate their cross-sections, figures out exactly how they share the energy, and then begins entirely new simulation tracks for these two brand new particles. It's like a chain reaction of math.
Let's see how all of this builds into our final section, running the code.
With all the physics and probability mapped out, how do we actually pull the lever on this massive slot machine? Well, to run a robust program like EGSnrc, the user has to supply 2 essential files. First, you've got the input file. This is where you tell the software about the exact geometry of your phantom, the energy of your photon source, and exactly how many millions of histories you want to run. Second is the PEX file. This file contains all the parsed material data, the densities, the cross-sections, the stopping powers, all that stuff we downloaded earlier from the NIST and EPICS databases.
A massive part of creating that input file is getting the geometry right. Honestly, it's about 50% of the actual work. In EGSnrc modules like dosimetry, you build your patient or your water phantom slice by slice. It visualizes the geometry as a highly customizable series of concentric cylindrical slabs. You meticulously define which cylinders are air, which are water, and which are bone. And only when that physical space is perfectly constructed do you finally unleash your millions of simulated photons.
Which brings us to a final, pretty incredible thought. How does relying on massive computational probability change the way we treat real-world medical physics? Well, by bridging abstract stochastic math with applied atomic physics, Monte Carlo transforms random chance into the exact precision needed to safely treat cancer with radiation. Every single interaction, every atom, every millimeter is strictly accounted for through the sheer power of probability.